Okay, let's go ahead and do some problems that calculate delta G and then use delta G in order to be able to figure out temperature. So let me just go ahead and do this because it seems like I get things going if I do it. All right. So we have this problem over here. We have a chemical reaction. N2 plus O2 goes to form 2N2O5. And you have a delta H for it. It's an exothermic reaction. The enthalpy change is negative 42.3 kilojoules per mole. And I have that right here. And the entropy change, the delta S, is negative 183.2 joules per mole Kelvin. Given that already. You don't have to calculate it. There are ways of calculating using entropies of formation, product minus reactants, stuff like that. And these looks like you'll be given them in this chapter. So the question is, what is the delta G? We're looking for a delta G. What is the delta G for the reaction above at 75 degrees Celsius? There's a temperature right there. So let's figure that one out first. Let me go ahead and go back to the black pen. We're going to use the equation delta G is equal to delta H minus T times delta S. Okay, and remember, we want to see what delta G is. If it's negative, it's spontaneous. If it's positive, it's not spontaneous. So our delta G going to equal to delta H. And one thing I want you guys to notice is that the delta H is in kilojoules per mole, and the delta S is in joules per mole Kelvin. Whenever you add or subtract two quantities, they need to be in the same units. Otherwise, you can't add or subtract. So in order to get all these units to be the same, it's kind of like adding kilograms to grams. You can't do that unless you turn the kilograms to grams or vice versa. What I'm going to do is I'm going to turn the kilojoules into joules. And so negative 42.3 kilojoules per mole. I'm going to go ahead and convert the kilojoules into joules. Remember the prefix kilo means 1,000. So kilojoule is 1,000 joules. So I'm going to go ahead and put 1 kilojoule on the bottom here, 1,000 joules on top. And so kilojoules cancel. Negative 42.3 times 1,000 is going to give you negative 42,000. Two's not looking too good. 42,300 joules per mole. All right, so that's what I'm going to use for my delta H. Negative 42,300 joules per mole. Okay. Minus T delta S. First off, the T has got to be in Kelvin. You'll notice that the delta S here is in minus 183.2 joules per mole Kelvin. So I need my temperature in Kelvin. So in order to get Kelvin temperature, what I got to do is I'll take my degree Celsius, 75, add 273 to it, and I get, what do we get? 348. 348. There's my dysnumeria. 348. So that's my temperature. So that's 348 Kelvin times delta S. And delta S here is negative 183.2 joules per mole. So first thing I got to do is multiply these two out and get an answer right there. And I'm going to go ahead and do that. 348 times negative 183.2 is going to give you negative 63,753. So give you, combine those together, negative 63,754. Notice that the kelvins cancel here and leaves you joules per mole, which are the same units as your delta H. Right? So I have negative 42,000. I did nothing with the delta H. 300 joules per mole. So as you can see, these two have the same units, so I can subtract them from each other. Joules per mole, joules per mole. Okay. So now I have negative 42,300. And do negative 42,300 minus a negative 63,754. So if I go ahead and add those two together, right? Subtract the negative, I'm going to end up with positive 21,454. 454. And that's going to be joules per mole. And so there would be your answer. And that makes this reaction at this temperature, that makes it not spontaneous. If I want to answer this in kilojoules per mole, or if you'd been asked to answer it in kilojoules per mole, then I can just go ahead and convert it. 21,454 joules per mole times, and there's 1 kilojoule for every 1,000 joules. And that's going to give me 21.45, 21.5 kilojoules per mole. So that's the way you'd answer it in kilojoules. Regardless, in both cases, it's positive, and so therefore this reaction will not be spontaneous at this temperature. More like the reaction will be the reverse, and 2O5 breaks up into and O2 at this. Okay, so you got that. Basically, just plugging in, right? You were given colors again here. You were given a delta H. You just turned it into joules per mole, converted it from kilojoules to joules. You were given a temperature, and you were given a delta S. Multiply the two things together. In this case, it gave you a negative answer. And then so you take a negative delta H there. You subtracted a negative number. There's your T times delta S. And since this one was a bigger negative than this one was, when we subtracted that bigger negative, we ended up with a positive answer. Okay. All right, so that's the first part of the question. What is the delta G for the reaction? Let's try the second part. At what temperature is it at equilibrium? I'm going to move this down. Okay, I'm going to move this down. Up, this whole problem up, and move this down a little bit. If you want to go ahead and see what we did before, you can go ahead and go up. All right, the second part of the question says, at what temperature is the reaction at equilibrium? So, what temperature is the reaction at equilibrium? How do we know what is equilibrium? We've barely learned about equilibrium. Equilibrium is when delta G is equal to 0. So what we're going to do is we're going to plug in 0 in our equation. Once again, we're going to use the same equation. Delta G is equal to delta H minus T delta S. And we're going to plug in 0 here. So 0 is equal to delta H minus T delta S. Let me fix that right there. That should be delta H. Okay. Minus T delta S. So our delta G is 0. We have delta H up there. We have delta S. All we have to do is find what the T is. So let's go ahead and plug those things in. So 0 equals to delta H. We already calculated this out for the earlier part. Delta H is minus 42,300 joules per mole. At this point, we're not using this temperature anymore. We're looking for the temperature when it's at equilibrium. So I'm going to leave this T as our variable, minus T, and delta S. Delta S we know is negative 183.2 joules per mole Kelvin. All right. So in order to solve for this, here's the negative. I'm going to go ahead and move this to the left. In other words, what I'm going to do is I'm going to go ahead and add T delta S here. 3.2 joules per mole Kelvin. So they cancel on the left, on the right. And then I'm going to add them on the left. Add T times negative 183.2 joules per mole Kelvin. All this should be on the left of the equal sign. I need to move this over a little more, over a little bit more. Let me go ahead and clean this up a little bit. That's the nice thing about having this whiteboard here as opposed to on a piece of paper where you've already written the edge. Okay, there you go. Back to doing this. So I'm going to add the T times the delta F minus 183. I figured I'd get better at using this little contraption here. Is what joules per mole Kelvin. And this should be closed in here. So these guys are canceling out over here. And what I end up with here is T times negative 183.2 joules per mole Kelvin equals to negative 42,300 joules per mole. Okay. So once again, the only variable I have here is that T on the bottom over there. So let's solve for it. I'm multiplying it by negative 183.2, multiplying it by my delta S. So divide both sides by 183.2 joules per mole Kelvin. By negative 183.2 joules per mole Kelvin. So that these cancel out. Okay. And so what I'm going to get is that T is going to be equal to negative 42,300 divided by negative 183.2. So 42,300, negative 42,300 divided by negative 183.2 is going to give me 231. 231 is the answer here. 231. 231 what? Turns out it's 231 Kelvin. Oops, that should have been to begin with. Because you'll notice that joules per mole cancel here, joules per mole cancel here. We're left with 1 over Kelvin, and once again, the denominator of the denominator goes to the numerator. This one shouldn't have been here. It wasn't there before. Over here. So that's the temperature at which delta G is going to be 0, okay, for this reaction. And that's what we're looking for. What is the temperature at which the reaction basically goes from being spontaneous to not being spontaneous. The question is the temperature, is the reaction spontaneous above its temperature or below it? Is it at higher temperatures above 231 or below 231? You want to ask that question? The easy way I have of answering that one is to plug in a 0 for your temperature. Use the same equation. Delta G is equal to delta H minus T delta S. And if you plug in a 0 for temperature here, that means that the whole T delta S becomes a 0. So the sign of your delta G is just dependent on delta H at 0 Kelvin. When you plug in a 0 for your temperature, it doesn't matter what the delta S, no matter what the delta H is, this becomes 0. And so now the sign of delta G, the sign of delta G, I'm going to move this up a little bit, is going to be based the same as the sign of delta H. So here our delta H was negative 42.3. So therefore it's going to be negative and it's going to be spontaneous at less than 231 Kelvin. Now at 0, it's kind of an extreme case, but below 231, they're all going to be negative. Above 231, they're all going to be positive. So whatever the sign is at 0, that's going to be your spontaneity at any temperature below that temperature. Which basically just means that if your delta H is negative, like it is right here, the reaction is going to be spontaneous at temperatures below your equilibrium temperature. If your delta H is positive, your delta G is going to be positive at temperatures below this, and therefore it's going to be negative above it. So in this case, since we have a negative delta H, our reaction is going to be spontaneous below temperatures below this. There's your answer to this last part of this equation. Okay. Hopefully that was all clear. I was trying to spend time trying to get it all on the one board here. Remember, it's just using the same equation. So the main equation here to use was delta G equals to minus delta G equals to delta H minus T delta S. It might actually be easier to, instead of plugging in the numbers first, to move the letters around. And then once you've moved the letters around, plug in the numbers, especially when your delta G is 0. Because when delta G is 0, if you plug in 0 for delta G, then you have delta H minus T delta S. Instead of having to plug the numbers in, just go ahead and add T delta S to both sides. You're not adding things. And this works all the time. So you end up with T delta S. That cancels. T delta S is equal to delta H. Divide both sides by delta S. And you come up with a new equation. Your T, the delta S cancels here. T is equal to delta H over delta S when delta G equals 0. When delta G doesn't equal 0, that's not the case. But in this case, this is your equilibrium temperature right there. Okay, so I hope that's helpful, especially if you're doing the homework. And I hope now you know why some chemical reactions occur and sometimes they don't, or at least not spontaneous. Okay. All right. Thanks for listening.